Good evening everyone. My name is Devlina Maiti. I am a NPTEL TA for the course Basic Real Analysis, and this is the 12th problem solving session, and this is the last session of this course. In the last session we have discussed about pointwise convergence and uniform convergence of sequence of functions, and in this session we are going to discuss about series of numbers and series of functions. Okay, so let's start this session. So we already know about the sequence of numbers, right? So first let un be a sequence of numbers, sequence of real numbers, right? Now we define the sequence. Now the sequence Sn we are defined by so first S1 is what? S1 is U1 from this sequence, and S2 is what? S2 is U1 plus S2, S3 is U1 plus U2 plus U3, and this goes on, right? So what is Sn? Sn is the nth sum of this sequence Un, right? So this sequence is represented by the whole sequence by the symbol U1 plus U2 plus U3 to infinity, and this series this is said to be which is said to be an infinite series. This sequence Sn is this one, this U1 plus U2 plus U3 to infinity. So this infinite sum is said to be an infinite series, and this series is generated from the sequence Un. Infinite series generated by the sequence Un, right? So this series is generated by this sequence Un, and this series is denoted by this infinite sum. So this series is denoted by sum of Un, and the summation is from 1 to infinity, right? This is denoted by this one, and each of this element of the sequence Sn is what? Sn is the nth partial sum. So Sn is what? Sn is the nth partial sum of the series, this one, right? Sn is what? U1 plus U2 to Un. So it is the nth partial sum of this series, right? Now this infinite series is said to be convergent. Now this infinite series summation Un is said to be convergent or divergent according as the sequence. So this infinite series is convergent means what? The sequence Sn is convergent or not, right? Because this sum is actually the sequence Sn, right? The sequence Sn is the sum. So this infinite series is convergent means the sequence, as the sequence Sn is convergent or divergent, right? So the convergence or divergence of the infinite series depends on the convergence or divergence of the partial sums Sn, right? So now we'll see some examples. So the first one is this series is 1 by 1 plus 2 by 1 by 2 plus 3 plus 1 by 3 into 4 and so on, right? So you have to check if this this is a series, right? If this series is convergent or divergent, right? So check the is convergent or divergent, right? We can write this series as sum of un, right, equals to, so what is un? Un represent the nth term of this series, right? So it is 1 by, so the first term is 1 by 1 into 2, second one is 1 by 2 into 3, so the nth term will be 1 by n into n plus 1, right? So un is this. Now we can write this series. Now what is Sn? So for convergence of divergence of this series, we have to check the sums, partial sum. The sequence we have to find, this one. So it is convergent or divergent if this sequence is convergent or divergent, right? So what is Sn here? So Sn is nth partial sum up to n, un, u1 to un. So it is n into n plus 1, right? So we can write 1 by 1 into 2 by 1 minus half, and 1 by 2 into 3 by 1 by 2 minus 1 by 3, and 1 by n into n plus 1 by 1 by n minus 1 by n plus 1, right? Now these are cancelled, this will be cancelled out, right? Oh no, not this one, sorry, this one will be cancelled out. So we will be left with 1 by 1 minus 1 by n plus 1, right? Now this is our sequence Sn. Now this means Sn goes to 1 as n goes to infinity, right? So this Sn sequence is convergent. So limit n tends to infinity, Sn equals to 1. This means the sequence Sn is convergent, right? This implies the infinite sum, the series, is also convergent. This is the same thing, right? So this is convergent. Alright, so this sum is convergent, means it is it gives some finite value, not infinity. Means it is equal to some finite value. Right? Let's go to the next problem. So take this sum 1 plus 2 plus goes to infinity, right? So is this convergent? So we'll write it by the infinite sum un, right? So un is what? Un is n here. Now what is the partial sum? Sn. Nth partial sum is up to n, and we know this value, which is n into n plus 1 by 2, right? So Sn is this number. Now we see that this number, this function of n is not convergent, because as n tends to infinity, Sn goes to infinity. Sn goes to infinity, right? So it is not convergent. So the sequence Sn is not convergent. This means the sequence Sn is not convergent. Therefore, the sum un is not convergent. Right? Okay. So let's check another example, which is this 1 minus 1 plus 1 minus 1 plus 1. So it is oscillating between plus 1 and minus 1, this sum. So is this sum convergent or not? So this means, is it convergent or not? Right? So first we will write it as un, n equals to 1 to infinity, right? So here the nth term will be either plus 1 or minus 1, right? So un here is plus 1 if n is even, if n is odd, then it is 1, and minus 1 if n is even, right? So it is actually minus 1 to the power n plus 1, right? So un equals to minus 1 to the power n plus 1. Now what is Sn? Sn is the nth partial sum. So Sn will be, Sn is u1 to un, right? So if n is even, then it is 0. If n is even, it will be 0, right? And if n is odd, then it will be 1, right? And the other terms will be cancelled out, right? So Sn is 0 or 1 if n is even. So what is this sequence Sn? So Sn is, so if n is even means first u1, s1 is what? S1 will be 1, s2 will be, n is even, so it is 0. So it is oscillating between 1 and 0. So this sequence Sn is not convergent. So that means the series, this one, the sum of un is also divergent, right? So this means the sequence Sn is divergent So this implies summation un, the infinite series, is divergent. Right? So this series is not convergent. Okay, let's go to the next one, which is the geometric series. So the geometric series is actually 1 plus a square plus so on, where mod a is strictly less than 1. Right? So for this series, what is our Sn? Sn is 1 plus a to the power n minus 1. The first n terms of this series, right? That is Sn, the nth partial sum. So the value is what? 1 minus a. Since mod a is less than 1, right? Now this is equal to 1 by 1 minus a to the power by n by 1 minus a, right? Now since mod a is less than 1, as n tends to infinity, a to the power n will goes to 0, right? So limit n tends to infinity, Sn is which is 1 by 1 minus a, right? So the sequence of partial sums Sn converges when mod a is less than 1, right? Therefore summation, or we can say the series sum of a to the power n equals to 0 to infinity, converges for mod a less than 1, right? Now what happens if a equals to 1? So if a equals to 1, the series so becomes, so Sn will be then 1 plus n, which is n. So Sn will be n, which is a divergence sequence, right? So limit Sn is infinity. So then the series diverges. Now what happens when a is greater than 1? So then what is our Sn? So Sn will be then a to the power n minus 1 by a minus 1, right? Because a is greater than 1 now. Now here also, when n goes to infinity, Sn is infinity, right? Because a is greater than 1, so a to the power n goes to infinity. So here also Sn goes to infinity. Now what about a is equals to minus 1? So then Sn will be oscillating, right? This series. So Sn will be 0 if n is even and 1 if n is odd, right? So Sn is oscillating, this means it is divergent. So the sequence Sn is divergent. Now what about if a is less than minus 1? So if a is less than minus 1, Sn is a to the power n minus 1 by a minus 1, right? Then also limit Sn goes to infinity, right? minus infinity. Right. Or it will be minus infinity. No, there is a in the. It will be infinity. So this means the geometric series is convergent for mod A less than 1 and divergent for mod A greater equals to 1. Right. So it is convergent only for mod A less than 1. Right. Okay. Now there are some criteria to check if a sequence is convergent or if a series is convergent or not. So the first criteria is the Cauchy criteria or the Cauchy principle. So Cauchy principle of convergence. So what is this principle? So it is a necessary and sufficient condition for convergence of a series. So a necessary and sufficient condition for the convergence of a series. Suppose this un n equals to 1 to infinity is that given a p assigned positive epsilon, there exists a natural number m belongs to this n such that mod of s n plus p minus sn is less than epsilon for all n greater equals to m and for every p belongs to the natural number. And what is this Sn? Sn is the nth partial sum. Sn is the nth partial sum of this series un, right? So Cauchy principle says that un is convergent if for a given epsilon there exists a natural number m for which this inequality holds, right? Is n plus p minus sn for every n greater for every p belongs to n and for all natural number n greater equals to m, right? And using this theorem, using this principle, we are going to prove a theorem which is a necessary condition for convergence. So what is theorem 1? So theorem 1 says a necessary condition for convergence. So a necessary condition for the convergence of a series summation un is that the tail of this series that is un. The tail of this series has to go to 0. This is a necessary condition for the convergence of this series, that the nth term must go to 0 as n goes to infinity. Right? So we are going to prove this theorem. This is a simple proof using this Cauchy criteria. Right? So we'll use this criteria, Cauchy's principle. So first we have to take epsilon. So choose, or let epsilon be any, epsilon greater than 0. Right? Now it is necessary condition, means we are taking that this series is convergent. Right? So this series is convergent means for this given epsilon there exists m belongs to n such that this happens, this Sn plus p minus Sn is less than epsilon for all n greater or equals to m, and for every p belongs to this n. Right? For every p natural. This happens because as sum of this series is convergent. Right? So you are taking that this is convergent, then what happens? Right? So this is convergent, then this we are getting by Cauchy principle. Now since it is true for every p belongs to n, take p equals to 1. Right? So what we are getting then? Then we are getting Sn plus 1 minus Sn is less than epsilon for all n greater or equals to m. Right? Now what is Sn? Sn is the nth partial sum. So Sn plus 1 is the n plus 1th partial sum. So this is what? So Sn plus 1 minus Sn is what? Un plus 1. So it is actually un plus 1, which is less than epsilon for all n greater or equals to m. And from the epsilon definition of limit, we can say that limit n tends to infinity un equal to 0. Right? Because this means what? This means limit un is 0 means given a positive epsilon, there exists a natural number m for which mod of un minus 0, that is mod un, is less than epsilon for all n greater or equals to m. Right? This is actually this line. So that's why we are writing limit n tends to infinity un is 0. Right? So we have taken that this series is convergent and we are getting limit un is 0. Right? So if a series is convergent, then the nth term must go to 0 as n goes to infinity. Right? Now if we look at this example, this one, this exercise 3, we can see that what is un? Un is 1 or minus 1 if n is even or odd. So un does not go to 0 as n goes to infinity. So this series cannot be convergent. Right? And we have also proved that this is divergent. Right? Also for this example, exercise 2, we see that un is n. Right? So as n goes to infinity, un goes to infinity. So this series also cannot be convergent. And we have also proved that here that this series is not convergent. Right? So if we know this theorem, we could have said that examples are divergent by a single line. Right? Okay. Now is the converse true? Means is it sufficient enough to show that it is it is also a convergent series. So what I am trying to say is that let UN be a series and limit UN is 0. As n goes to infinity, it is 0. Now does it imply sum of this UN is convergent? The answer is no. So you have to give a counter example, right? So take UN to be 1 by n, right? So what is the series? So the series is 1 plus 1 by 2 and so on, right? So now you can clearly see that as n goes to infinity, UN goes to 0. So this condition is satisfied. Now the question is if this series convergent or not. So choose epsilon to be 1 by 3, right? And here we see that the Sn is the nth partial sum. So Sn plus p minus Sn here is what? Sn is n plus pth term and Sn is 1 to u1 plus u2 to un. So it is un plus 1 to un plus p, which is nothing but 1 by n plus 1 plus 2 to 1 by n plus p, right? Take p equals to n. P is any natural number. You can choose p to be n, right? So then mod of s n plus p minus Sn, this is actually s to n minus Sn is 2 1 by 2n, right? Now n plus k is less than n plus n when k is less than n, right? So n plus k is less than 2n, and which means n plus k is strictly greater than 1 by 2n when k is less than n, right? Now if we use this in this line, so what we will get? We'll get Sn plus p minus Sn, and for each k less than 1, so 1 by n plus 1 is also greater than 1 by 2n, n plus 2, 1 by n plus 2 is also greater than 1 by 2n, right? So it is greater than 1 by 2n plus 1 by 2n. So we are replacing each 1 by 1 plus k, n plus k by 1 by 2n, right? So there is n term, so it is n by 2n, so which is 1 by 2. Now we see that by Cauchy criteria, so it contradicts the Cauchy criteria, right? So we have found a n which is found a p. So in Cauchy criteria we are given that this has to be true for every p, right? For every p this has to be satisfied, right? Now we have found a p which is n for which this difference is greater than our epsilon. So we have found a p which is n for which this difference is n plus p minus Sn is greater than half, which is greater than 1 by 3. That is our epsilon. So by Cauchy criteria, it is not convergent. So this implies the sum of 1 by n equals to 1 to infinity is is divergent by Cauchy principle, Cauchy criteria, right? So this sum of 1 by n is divergent. Okay. Now there are some tests for this to test the convergence of this non-negative series, right? So we'll discuss about some test for convergence of a non-negative series. Non-negative series means each of the term of the series is non-negative, right? So the first test is comparison test. So it is clear from the name that we are going to compare two series, right? So let x is a sequence xn and y is this sequence yn, right? And suppose 0 less equals to xn less equals to yn for n greater equals to k, right? So there are two sequences and they follow this rule, right? That 0 less equals to xn less equals to y, right? Then this yn converges this sequence, the bigger one. If this sequence yn, the sum yn converges, then this will imply this series is also convergent, right? This series converges. If the bigger one converges, then the lower one, the smaller one will also converge, right? And the other one is that if the smaller one diverges, then the bigger one will also diverge, right? And there are another test which is the limit comparison test. So what does it say? It is also comparison, so there will be two sequences. So x is xn and y is yn, right? These two sequences, and they are strictly positive sequence. So for comparison we have taken non-negative, this is greater equals to 0, but for limit comparison both the sequence has to be strictly positive. So it is strictly positive sequences, and suppose that limit n tends to infinity, xn by yn exists, and let r equals to n tends to infinity xn by yn, right? So you are saying that this limit exists, right? And this is equals to r, right? Then if r is non-zero, then then summation xn, this sequence converges if and only if this sequence is also converges, right? So this implies if r is non-zero, this means both the sequences converges and diverges simultaneously, right? And there is another condition, another one, which is when r is 0. So if r is 0, if yn converges, then xn also converges, right? Okay, so we'll see some examples where we'll use this test to see if this series is convergent or not, right? So the first one is test, or we have to show the series n equals to 1 to infinity 1 by n square minus n plus 1 is convergent, right? So we'll use this test, comparison test or limit comparison test. So first, so we have to choose two sequences. So one has to be this sequence. So let xn be 1 by this one. And what should we take this y1? So choose y1 to be 1 by n square, right? Now limit n tends to infinity, xn by yn is what? N square by n square minus 1 plus 1, which is 1, right? So by limit comparison test, we are seeing that this r exists and this is 1, non-zero. So this means both the series converges or diverges simultaneously. Now this sum, this yn, is convergent. Why? Because this series, this summation n equals to k equals to 1 to infinity, n equals to 1 to infinity n to the power p converges for p greater than 1, right? And diverges for p less than 1, less equal to 1, right? So this implies this sum 1 by n square is convergent, right? So by comparison, by limit comparison, by limit comparison test summation xn, this means summation 1 by converges, right? Okay, so let's take another example. So test the convergence of this series which is given by 1 plus 2 by 1 plus 2 by 2 power 3 by 3 power 3 4 power 3 and so on, right? So you have to test the convergence of this infinite series. So what is un here? The nth term. So suppose this is equals to sum of un, right? So what is un then? Un then 1 plus 2 2n, sorry, this is n plus 1, because second term the numerator is 1 plus 2 plus 3, right? So it goes to n plus 1 and the denominator is n plus 1 power 3, right? So it is which is n plus 2 by 2 into n plus 1 whole square, right? So it is our un. Now we'll use comparison test. So we'll choose bn to be 1 by n, right? So you're choosing bn to be 1 by n. Now let's check this number un by vn. So it is n into n plus 2 by 2 into n plus 1 whole square. So which is, if we divide the numerator and denominator by n square, we'll get 1 plus 2 by n, and here 1 plus 1 by n whole square, right? So this value, when n goes to infinity, this value is going to be 1 by 2. So this r, this limit comparison test, this r is non-zero. So this means they converge or diverge simultaneously. So now this Vn, which is 1 by n, so it is a divergent series, right? This is divergent series. Here we have already seen this, right? P equals to 1. So since this series divergent and R is non-zero, this implies the main series, this un, sum of un, is also divergent. Right? By limit comparison test. Okay. Okay, now we will discuss about absolute convergence of a series. So what is absolute convergence? So let x equal to xn be a sequence of real number, right? So we say that the series summation xn n equals to 1 to infinity is absolutely convergent if the series to infinity mod of xn is convergent. Okay. If the modulus of this main series is convergent, then we say that the main series is absolutely convergent, right? And we can prove that if this is absolutely convergent, if a series is absolutely convergent, then the main series is also convergent. And there is another convergence which is called the conditionally convergent series, which is said to be convergent. So if this is not absolutely convergent, we say that it is conditionally convergent. So it is said to be conditionally convergent if it is convergent. First, it has to be convergent, but it is not absolutely convergent. Right? And also, here note that this is a simple proof. Absolutely convergent implies convergent. Means if summation mod of xn is convergent, then summation xn is convergent, right? This is a simple proof. Just use the Cauchy criteria and triangular inequality. Okay. This is a homework. Now there are tests to show if it is absolutely convergent or conditionally convergent, like ratio test and like this limit comparison test and comparison test. So there are tests to check if this convergence is absolute or not, right? So the first test is the root test. So let x be this sequence in R, right? Then this test says if there exists R, a real number with 0 less than R, or there's only R less than 1 and K belongs to N, such that modulus of xn to the power 1 by n is less than r is equal to r for n greater equals to k, then to infinity xn is absolutely convergent, right? And the second result is, if there exists k, a natural number, such that mod of xn to the power 1 by n is less than 1, strictly less than 1 for all n greater equals to k, then xn is convergent. This is convergent, not absolutely convergent. If this B happens, right? And there is another test which is called the ratio test. So what is this test? So again, let x equals to xn be a sequence, and this sequence is a non-zero real number, sequence of non-zero real numbers. For root test, there are no issue of non-zero or not, because we are taking modulus of xn, right? So it becomes positive. So here we are taking a sequence of non-zero real numbers, and then the first condition says, if there exists r, a real number with 0 less than r less than 1, and k belongs to natural number such that this ratio xn plus 1 by xn modulus is less equals to r for n greater equals to k, then this series is absolutely convergent. Right. And the second one says, if there exists k, a natural number, such that this ratio xn plus 1 by xn is greater equals to 1 for n greater equals to k, then this sum xn, this series is divergent, right? These are two tests for checking absolute convergence or not, right? So absolute convergence means this modulus is convergent, right? And conditionally convergent means it is convergent but not absolutely convergent, right? So we'll see some examples to understand this. So the first example is, check this series. Right. So you have to check if this series is absolutely convergent or not, right? So we'll use this test. So we'll test, right? So what is un or xn? Q plus 2 whole to the power n, right? This is our sequence un, right? So for this we'll use the root test, because there is power to the power n, and in root test what we do modulus to the power 1 by n, right? And this r has to be less than 1. So here what is modulus mod un to the power 1 by n is 5n minus 3n cube by this number, right? Modulus of this number. Now this has to be less than 1 to be absolutely convergent. So limit n tends to infinity is what? So as n tends to infinity, so this number will go to minus 3 by 7 modulus of, so this is 3 by 7, which is less than 1, right? So by root test, so limit term is less than 1, so all the terms, so limit is less than 1 means, so after some k, all the after some k, limit is less than 1 means there will be some k, after that all the terms will be less than 1, right? Less than this 3 by 7, which is strictly less than 1, right? So by root test, this sum, this series is absolutely convergent, means the modulus is convergent, right? Okay, let's see another example. So take this sum n equals to 2 to infinity n square by 2n minus 1 factorial. So check if it is absolutely convergent or not, right? So un, the sequence is here, what? This is n square by 2n minus 1 factorial, right? Now for this example, we'll use the ratio test, right? So what is un plus 1 by un? So it will be modulus right? So this is square by n square into 2n plus 1 into 2n, right? So this will go to 0 as n goes to infinity, right? So this means what? This means from the ratio test, since this goes to 0, there exists some k after which all this term is going to be 0, right, which is strictly less than 1. So by ratio test, this is absolutely convergent, right? So by ratio test, this sum un is absolutely convergent, right? Okay, let's take another one. So take this sum. So it is 1 by 2 plus 1 by 3, 1 by 2 square plus 1 by 3 square, and like this. So you have to check if it is absolutely convergent or not. So we'll use the ratio test or root test. So we are denoting un, sum of un, to be this number, this sum. Right. So then, what is u2n? This means the even terms. 0, oh sorry, this is 1. So this one, this is this one, this one, and this one. So u2n's are what? 1 by the first one, u2, is 1 by 3. That is u3 to the power n, right? And u2n plus 1 is what? 2n plus 1 means if n is 0, it is u1, and then u3, u5, like this. So the first term is 1 by 2. So this means it is u2 to the power n plus 1. Because when n is 0, means u1 is 1 by 2. Right? And u2n minus 1 is, minus 1 means it starts from n equals to 1. So when n equals to 1, it is u1. Right? So when n equals to 1, it is u1. u1 is 1 by 2. So this is 1 by 2 to the power n. Alright. So now by ratio test, what we are getting, if we take limit n tends to infinity, u2n by u2n minus 1, because there we choose xn plus 1 by xn, right? So here we have chosen u2n by u2n minus 1, right? So we are not taking the modulus because each of this term is positive. So it is what? It is limit n tends to infinity. u2n is 1 by 3 to the power n, and u2n minus 1 is 2 to the power n. So it is n tends to infinity 2 by 3 whole to the power n, and since 2 by 3 is less than 1, so it is actually 0. Right? So here we have taken u2n by u2n minus 1. Now if we take u2n plus 1 by u2n, then what will you get? We'll get u2n plus 1 is 1 by 2 to the power n plus 1, and u2n is 1 by 3 to the power n. So it is 3 to the power n. So it is basically 1 by 2 or 1 by 3 into 3 by 2 whole to the power n plus 1, right? So it is 1 by 3, limit n goes to infinity, 3 by 2 whole to the power n plus 1. Now since 3 by 2 is greater than 1, this limit will go to infinity, right? So this is infinity. So what we are seeing is that limit supremum of un plus 1 by un is supremum value is infinity and infimum value is 0, right? This one, because we are getting 0 and infinity, so the supremum has to be infinity and the infimum is 0. So by ratio test, this, what we have to find, we have to find this is less than some number r which is lies between 0 to 1. But we are getting what we are getting, it is the supremum value is infinity and the infimum value is 0. We cannot say about all the terms, right? So this ratio test here gives nothing. So this means ratio test gives no decision, right? So we cannot decide anything. It varies from 0 to infinity, but we cannot say all the values is less than some number r which is less than 1, right? So it gives no decision. So ratio test fails here. So now we'll use the root test, right? So for root test, we'll find limit n tends to infinity u to n whole to the power 1 by 2n, right? Which is u to n is 1 by 3 to the power n to the power 1 by 2n. So it is basically 1 by root 3, right? And limit n tends to infinity u to n plus 1 whole to the power 1 by 2n plus 1 is what? This is u to n plus 1 was 1 by 2 to the power n plus 1 whole to the power 1 by 2n plus 1. So it will be 1 by root 2, right? So the supremum value, so we are getting two values, and if we take this one u to n minus 1, so it will also give 1 by root 2, right? So the supremum value of this, so limit supremum of un to the power 1 by n is what? Supremum value is 1 by root 2, right? Means the bigger one. So the bigger one is less than 1. So this implies all the values, supremum value is less than 1. So this means all the values is less than 1, right? Strictly less than 1. So ratio test was what? Ratio test was if modulus of this is less than r, where r is some number which is less than 1, strictly less than 1, then it is absolutely convergent. This one or this one, b. From b it is convergent. Is strictly less than 1. So this means summation un n equals to 1 to infinity is convergent. We cannot say about absolutely convergent, because then it has to be less than since it is less than 1 by root 2, which is less than 1, it is also absolutely convergent, right? Right? So here we see that this root test is more powerful than this ratio test, right? So in this series ratio test fails, but the root test gives a decision if it is convergent or not, right? So your note is that root test is more powerful than the ratio test, right? Okay, so we have discussed about series of numbers, right? So now we are going to discuss about series of functions. In the last session we have discussed about sequence of functions, right? So since we know the sequence of functions, so the series of function is the similar thing like series of numbers. So we are going to discuss series of functions. So you already know about sequence of functions. So fnx is a sequence of functions, right? And we know the pointwise convergence and uniform convergence, right? Now we are defining, so like in the series of numbers, here the snx is what? The nth partial sum of this sequence, so which is f1x plus f2x to fnx, right? Now this sequence, this series, this fnx is what? This is f1x plus f2x to infinity, right? So this is said to be a series of functions and it is denoted by the sum of fn, right? And the sequence of partial sum is snx. So snx is what? Snx is the sequence of partial sum of this fn, right? So like in the series of numbers, we say that if this summation of fn convergent, if and only if this sequence snx is convergent, right? So if this sequence sn is, here this sequence is not a sequence of real numbers, this sequence is a sequence of functions. So sequence of function is, so there are two convergence, pointwise convergence and uniformly convergence. So if this sequence of functions is pointwise convergent on some domain D, on D, to a function S or Sx, then this sum, this infinite series is said to be pointwise convergent. And if this sequence of partial sum is convergent, pointwise convergent, and pointwise convergent to a function Sx, then this infinite series is said to be pointwise convergent on D. And similarly for uniform convergent, if this is if this is uniformly convergent, this sequence of functions, then it is said to be uniformly convergent. On D, right? It is convergent to where? To the sum function, this Sx, right? This Sx. Okay, so we'll see some example to understand this. Okay, so the first one is prove that the series of functions 1 plus x square is convergent on 0 less equals to x less than 1, but this convergence is not uniform. Right, this we have to prove. Now recall that if fnx converges to fx uniformly, excuse me, so you're saying is that the sequence fnx converges to fx uniformly, and each fnx is bounded. Then what can we say about this f function? So this fx is also bounded. Right? And the second one is, if each of fnx, each of this fnx is continuous, then the limit function fx, then fx is also continuous. This is the consequences of uniform convergence, right? Right? So we'll use this. So for this series, this is a series of functions, because each of this term is not numbered. Each of this term is a function, x square, x to the power n, right? So unx is what? This each of this function or fnx is x to the power n, right? So what is snx? The nth partial sum is what? This is 1 plus x to the power n, right? And since x is less than 1, this value is 1 minus x to the power n by 1 minus x 0 1. Right? So when n goes to infinity, snx is what? Is 1 by 1 minus x. Right? So this means it converges to 1 by 1 minus x pointwise, right? So this sequence snx converges to 1 by 1 minus x on 0 1 pointwise. Right. So this sequence converges means this sum converges to 1 by 1 minus x on 0 1 pointwise. Right. Now you see that Snx is what? Snx is 1 minus x to the power n by 1 minus x. Right. And since x is not 1, this Snx is bounded, right? Because it is actually 1 plus x to the power n minus 1. Right? So each Snx is bounded. And if this convergence is uniform, then the limit function Sx has to be bounded, right? So if this convergence is uniform, then the limit function 1 minus x has to be bounded, right? But this is not true. 1 by 1 minus x is not bounded on 0 1, but 1 by 1 minus x is not bounded on 0 1, because as 1 x goes to 1, it goes to infinity, right? So this implies the convergence is not uniform. Right? So you have proved this one. So it is convergent, but the convergence is not uniform by this one. By the consequences, we have used this. Right? Okay, so let's go to the next example. Where x belongs to closed 0 1. This is not uniformly convergent on 0 1. Right. So I have to prove that this is not uniformly convergent. So first we will see the nth partial sum. So the nth partial sum is what? f1x plus 2fnx. So first one is x to the power 4. Sorry, this is, and the nth term will be x to the power 4 by 1 plus x to the power 4 whole to the power n minus 1. Right? And this is equal to x to the power 4 into right. This is our Snx. Now when x equal to 0, we put here x equals to 0, Sn x will be 0, right? And when x lies between 0 to 1, so when x is non-zero means x is lies between here, then our Sn x equals to x to the power 4 into this sum will be, this will be 1 minus x to the power 4 by n, and the denominator will be, right? So this is equal to into 1 plus x to the power 4 by x to the power 4, right? So since x is non-zero, we are cancelling it, so we get this Sn x equals to, when x is non-zero and less than 1, into 1 minus 1 by all to the power n, right? So this is our Sn x. When x is between 0 to 1. Now if we tend n to infinity, we will get what? This term will go to 0, right? When n goes to infinity. So this is 0 when x equals to 0 by this one, and when n goes to infinity, this for non-zero, this term will go to 0 as n goes to infinity. So this will give 1 plus x to the power 4 when 0 less than x less equals to 1, right? So we get our limit function. So Sx, we defined Sx to be 0 when x equals to 0, 1 plus x to the power 4, and x is non-zero. So this implies this sum, the series Snx converges to Sx pointwise, or we can say this Fnx converges to Sx pointwise on 0, 1, right? Now to show that this convergence is not uniform, right? Now we see that each of this Snx is what? Snx is this one. This is our Snx, right? You see that each of this Snx is continuous, right? This function, this one is continuous on open 0 to 1, right? Now when x goes to 0, now limit x tends to 0, Snx is what? If we here 10x goes to 0, then we'll get 1 into 1 minus 1, right, which is 0, and which is equals to S0. We have already seen when x is 0, then x is 0, Snx is 0, means Sn0 is 0, right? So I have found that limit x goes to 0, Snx is S0. This means Snx is also continuous. Snx was continuous on open 0 closed 1, right? Because this function is continuous, Snx, when x is non-zero, and we have seen that when x goes to 0, Snx coincides with S0. So this means Snx is continuous at x equals to 0. So each Snx is continuous on 0 1, close 0 1, right? But what about the limit Sx? So but Sx here, we see that Sx, this is our Sx, which is not continuous, because limit x goes to 0, Sx is 1, which is not equals to S0, right? So Sx is not continuous, right? And we have seen from the consequences of uniform convergence is that if the convergence is uniform and each of this function is continuous, then the limit function, the sum function, will also be continuous. And here we see that each of Snx is continuous, but the limit function is not continuous. So the convergence cannot be uniform, right? So this implies the convergence is not uniform, right? Okay. Now there is a test, like in the sequence of function we have there was M test, right, for sequence of function. Now here for series of function we have Wester's M test. Wester's M test. And what is that? So let D is a subset of R and this is a series of functions, right? Fnx V, series of functions on D to R. Now let Mn be a sequence of numbers, be a sequence of positive real numbers, such that for all x belongs to D, mod of Fnx is less equals to Mn for all n belongs to n, right? If this happens and if the series of real numbers, this Mn, is convergent, then the main series summation Fnx is uniformly convergent. On D, right? So this is like a comparison test, right? So you are saying that Fnx is, for each n, Fnx is less equals to some Mn, right? And you are collecting all these Mn's, so this gives a series of real numbers, right? And we are saying is that if this series is convergent, this Mn, then the main series summation Fnx is uniformly convergent on D, right? this is our Wester's M test. So we'll use this to solve some problems, right? Then we'll understand. So the first one is prove that the series summation 1 by n cube plus n to the power 4 x square is uniformly convergent for all real x, right? So we'll use Wester's M test. So here fnx is what? Fnx is 1 by n cube plus n to the power 4 x square, right? So for this we have to find mod of fnx is less than some number. So here we see that mod of fnx equals to 1 by, will always be less than 1 by n cube, right? For all x belongs to R, and for each n and for all x this will happen, right? Since this is bigger than 0, so this value will be less than 1 by n cube, right? Because this is greater than 0. So here what is our mn? So mn is 1 by n cube. So we have found that mod of fnx is less equals to mn for all x belongs to R and for each n in the natural number. Now this M test says if this series summation mn is convergent, then the series fn is uniformly convergent. Now summation mn is what? Summation mn is 1 by n cube. Since the power of n is 3, which is strictly greater than 1, so this is convergent, right? So this implies summation fnx is uniformly convergent. Right? For all real x. Right? So we have proved this by Wester's M test. Right? Okay, so let's take another prove that this sum, the series of functions x by n plus n square x square is uniformly convergent for all real x, right? So here again we have to prove that this is uniformly convergent for all real x. So here fnx is x by n plus n square x square, right? So we have to find our mn. Mod fnx less equals to mn by Wester's M test. So we have to find that mn for this function. So when x equals to 0, fnx is 0, right? If we put x equals to 0, fnx is going to be 0. Now when x is non-zero, we'll use the thing that arithmetic mean is greater equals to geometric mean. Right. Now for which two values? So arithmetic mean of will take these two, n by mod x and n square mod x. Geometric mean of n by mod x and n square mod x. Right. So what is the arithmetic mean of these two? This is n by mod x plus n square mod x by 2, which is greater or equals to root over n by mod x into n square mod x. So this gives us n plus n square. Mod x square means x square, since this is positive, by mod x, which is greater or equals to, this 2 will be cancelled out, so it will be n to the power 3 by 2. Right? So this gives mod x by n plus n square x square is less equals to 1 by 2 into n to the power 3 by 2. Right? And what is this number? So this was our fn. Right? So this is actually mod of fnx. Right? So mod of fnx is less equals to 1 by 2 into n to the power 3 by 2. Now we'll take this to be mn. Right? So mn is 1 by 2 n to the power 3 by 2. And since the power of this n is greater than 1, so now summation 1 by n to the power 3 by 2 is convergent, implies summation mn is convergent. Right? And by then by this Wester's M test, this implies the main series is uniformly convergent. Right? So therefore, and this happens, so I am not saying written for x, so for x non-zero this is true, right, for all x. So this happens for all x belongs to R, right, and for all n belongs to n. So by Wester's M test, summation fnx n equals to 1 to infinity is uniformly convergent for all x greater or equals to 0. For all real x, not greater or equals to 0, for all x belongs to R. Right? And there, so since there is no time, I will do just write this as an exercise. So show that this series e to the power minus 2x by 2 square minus 1 plus e to the power minus 4x by 4 square minus 1 minus e to the power minus 6x and so on. This converges uniformly for all x greater or equals to 0. Right. Also here we will use the Wester's M test. Right. This is a simple exercise. Just choose. So here you will see that f n x is what? F n x is minus 1 to the power n e to the power minus 2nx by 4n square minus 1. Right? N greater equals to 1. So mod f n x is less equals to, since e to the power minus something is less than 1, so it is less equals to 1 by 4n square minus 1, and this is our mn. And this summation mn will be convergent, so the main and this mn is convergent because there is n square, right? Or we can do the limit test, limit comparison test, right? This is un and we'll choose bn to be 1 by n square, then we'll see that summation mn is convergent, right? And then fnx, summation fnx will be uniformly convergent, right? Okay, so I'll end this session here. Thank you.